So hello everyone, welcome to the channel. So in this video I'm going to show you downscaling MODIS NDVI 500-meter resolution to a 30-meter resolution by machine learning approach using Landsat 8 imagery in Google Earth Engine. So now let's get started. So vegetation indices such as the NDVI are critical for monitoring and assessing the plant health, land surface processes and ecosystem dynamics. So MODIS provides an NDVI at a coarse spatial resolution around 500 meters, which limits its applicability for detailed studies at the landscape or the farm scale. So to address this, a downscaling technique have been increasingly explored, so allowing the researchers to transfer the temporal richness of MODIS data to a finer spatial resolution using a high resolution sensors such as Landsat 8 imagery. So in this study, we propose a robust technique to downscaling approach using a linear regression modeling in Earth Engine to enhance the spatial resolution of MODIS NDVI data from 500 meters to 30 meters. So the process begins by selecting our region of interest and identifying a reference point for a time series analysis. And the Landsat 8 level 2 surface reflectance data and MODIS NDVI image were filtered for the same time range, and the cloud conditions were applied. And later the temporal join is performed to pair the MODIS and Landsat 8 imagery acquired within 3 days, ensuring a radiometric consistency. So each pair is used to extract the NDVI from both sensors, and this linear regression model is fitted using MODIS NDVI as a predictor and Landsat NDVI as a response. So this derived regression coefficients are then applied across MODIS NDVI time series, so to generate a predicted high resolution 30-meter NDVI imagery. And this linear regression technique is leverages the temporal density of MODIS and the spatial details of Landsat imageries, and resulting a downscaled NDVI provides a spatial detailed time series insight and enabling improved monitoring for applications in the precise agriculture, land degradation assessment, and forest health monitoring and urban vegetation dynamics. So now let me get back to Earth Engine. So now to perform our analysis, first we need to select our region of interest. For example, I'm going to navigate to my region of interest. So my region of interest is lying here in Jackson till the Snake River, which is mentioned here. So I'm going to draw my study region using this particular option here. So I'm going to click this option called draw a rectangle, and I'm going to draw a rectangle over my region of interest, and you can be able to see. So once you did that, I'm going to click this option called exceed, and next we're going to navigate to the top section here. We have this newly created variable called variable geometry. So I'm going to click this option, and inside this we have this latitude and longitude of this newly created studied region. So I'm going to copy this using Ctrl+C in my keyboard, and similarly I'm going to paste it inside this variable called area coordinates using Ctrl+V. So once you pasted your latitude and longitude of this study area, so in the next step we're going to convert this particular variable, which is holding the latitude and longitude of the study area, into a polygon using a variable called study polygon equals to earthengine.geometry.polygon. And I'm going to mention my variable here, that is area coordinates, referring to this particular variable area coordinates. So it's going to convert this particular variable into a polygon. So in the next step, I'm going to add this layer, that is I'm going to mention map.add layer study polygon with a default visualization parameter, and we're going to output the layer name as study area. And followed by, to center this particular layer, I'm going to mention this map.center object study area with a suitable zoom level. So let me turn this off. And similarly, in the next step, I'm going to fix an observation point over a specific agricultural land, so a particular farmland. So for that, I'm going to mention a variable called observation point equals to earthengine.geometry.point. So I'm going to mention the latitude and longitude of that particular farmland using this latitude and longitude of the value. So for example, I'm going to click to a satellite mode here. So I'm going to navigate to my the farmland of my choice here in order to perform the time series analysis for the NDVI value. So I'm going to navigate to this particular farmland. So for example, this particular farmland. So we're going to place my observation point over this particular farmland. So to create your point, we have to navigate this option called add a marker. So we're going to click this option called add a marker. I'm going to turn this off here. So let me delete this particular polygon I have created earlier. So in the next step, I'm going to navigate to this option called add a marker, and I'm going to place a marker over this particular farmland. So now a new variable was created, geometry. So it's going to hold the latitude and longitude of this particular point over this farmland. So I'm going to copy this latitude and longitude using, I'm going to copy this. So once you copied it, I'm going to paste it inside this variable called observation point. So I'm going to paste it inside this variable called observation point. So basically I'm using this point data in order to perform the time series analysis for our NDVI for both Landsat 8 and MODIS NDVI image. So for that we are using this point. So once you placed your point, in the next step I'm going to turn this off. So in the next step I'm going to turn this off here. And to add this point, I'm going to mention this map.add layer observation point with the default visualization parameter, and output the layer name as observation point. So now let us visualize this particular layers here. Let me zoom out, and I'm going to navigate to the layer section. I'm going to turn on the study area. So this is my region of interest, and followed by my observation point. Let me turn this off, this layer off, that is study area, and I'm going to turn on the observation point. So now here I can able to visualize we have this point data, so which is lying here. So let me show you that. I'm going to zoom in here. So this is my point data, and turn to a map mode, so you can able to see the point data here. So in the next step we have to fix our time period of our analysis. For example, my time period of analysis is going to start from 2020 to 2021. So to fix the time frame for our analysis, we're going to define a variable called start date equals to 2020 and the end date is equals to 2021. So in the next step, we're going to load our Landsat 8 imagery, and we're going to visualize the WRS path and WRS row of this Landsat 8 imagery over the study region. So for that, we're going to define a variable called Landsat 8 equals to Earth Engine image collection Landsat LC08 C02 T1 L2. So this is the code to access the Landsat 8 imagery. Let me show you this particular imagery. So this is USGS Landsat 8 level 2 collection 2 and tier 1, and the dataset availability is from 2013 to 2025, and the dataset provider is USGS, and followed by, to access this particular data, we have to use this particular code to access the Landsat 8 imagery. And these are the following bands that is available in this dataset here, starting with SRB1 to SRB7. And here ST is the surface temperature, B10 data, that is thermal band. So these are the following bands that is available inside this data set. So let me get back to Earth Engine. So the next step, we're going to filter based on our region of interest, that is study area. We're going to mention as dot filter bound study polygon, referring to our study area, and followed by, we're going to mention this particular function called dot filter date based on the time period of analysis starting from start date to end date. So between this date, we're going to fix the analysis period. So we're going to mention this dot filter date, start date and end date, and followed by, we're going to apply a particular condition in order to get a satellite imagery with the least cloud contamination. So we're going to mention dot filter Earth Engine dot filter dot less than cloud cover, so cloud cover less than 10. And last, to visualize the metadata property of this particular data imagery, we're going to mention print Landsat 8 referring to this particular variable, and we're going to output the layer name as meta properties. So now I'm going to run this code here. So I'm going to click run. So now let us take a look at this imagery here, that is image collection Landsat. So in that, we're going to click this option called features. So in the features, we have a lot of imageries available for this specific study region from 2020 to 2021. So we're going to click the first image here, and in that I'm going to visualize the properties here. So these are the metadata property of this particular Landsat 8 imagery. So inside we have this WRS path and WRS row. So for example, this particular imagery has a WRS path of 39 and WRS row of 30, and followed by the second imagery. I'm going to click the second imagery, and I'm going to select this particular properties. I'm going to navigate down here, and here we have the WRS path is 39 and WRS row is 30. So once we have the WRS path and WRS row, that is 39 and 30, next we're going to apply this filter based on the row and path. So in the next step, we're going to load and pre-process the Landsat 8 imagery. So first we're going to create a variable Landsat NDVI equals to Earth Engine dot image collection Landsat LC 8 CO 2 T1 L2, and we're going to filter based on study area dot filter bound study polygon. Study polygon refers to our study area. And next step, we're going to filter based on the start date and end date using dot filter date, start date and end date. And the next step, we're going to filter based on WRS path and row. So we're going to mention dot filter Earth Engine dot filter dot equal WRS path 39, and next is the filter Earth Engine dot filter dot equal WRS row is 30. And the next step, we're going to apply the filter with the cloud contamination less than 10. So we're going to mention dot filter Earth Engine dot filter dot less than cloud cover 10. So in the next step, we have to apply the scaling and offset factor. So in order to perform analysis, we have to first apply the scaling factor. So let me show you the scaling factor here. So these are the bands, and we have the scaling factor of 2.75 into 10 power minus 5 is a scaling factor, and the offset factor is around minus 0.2. So we have to apply both the scale and offset factor in the imagery before proceeding towards the analysis. So to do that, we're going to mention a function here, that is the map function image, and inside we're going to mention the variable gain is equals to Earth Engine number and image get reflectance multiband. So for example, the reflectance multiband, so in the metadata property of this imagery, you can able to see the reflectance multiband is 0.0000275, so which is referring to this particular one, that is scale factor. And similarly, next is a variable offset is equals to Earth Engine number image get reflectance add band 3. So the reflectance add band 3 refers to this particular value, that is minus 0.2, which refers to the offset value, that is minus 0.2. So now we have to apply both scale and offset value. So to do that, we're going to mention variable surface reflectance is equals to image dot select SRB. So we are referring to all the bands in the Landsat 8 imagery, and we're going to multiply by gain, that is 2.75 into 10 power minus 5, and dot add, that is offset factor minus 0.2. So once we applied the scale and offset value, next we can perform our analysis. So the next step, we're gonna perform the NDVI. So NDVI using SRB5 and SRB4 band. So SRB5 here refers to, that is SRB5 refers to the near infrared band, and SRB4 which refers to the red band. So we're going to use these two bands in order to generate the NDVI. So to do that, let me navigate the Earth Engine. I'm going to mention a variable called NDVI Landsat is equals to the surface reflectance, referring to this particular variable where we applied the scale and offset value, and we're going to mention dot normalize the difference SRB5 and SRB4, which is referring to SRB5 minus SRB4 divided by SRB5 plus SRB4. So it's going to give us the normalized difference vegetation index, and we're going to rename as NDVI Landsat. And last, we're going to return as NDVI Landsat dot copy properties image. So it's going to copy the metadata property of this imagery to this particular image, that is NDVI Landsat. And the next step, we're going to load our MODIS NDVI collection. So to load our MODIS NDVI collection, we're going to mention the variable called MODIS NDVI equals to Earth Engine image collection MODIS mode 09GA006 NDVI. So this code, using this code, we can access our MODIS NDVI imagery. So let me show you this particular imagery, MODIS Terra Daily NDVI, and the dataset availability is from 2000 to 2023, and the dataset provider is Google. So using this particular code, you can access this particular dataset, that is MODIS Daily Terra NDVI image. So resolution of this particular imagery is around 500 meters of resolution. So this is a band, NDVI band, which is provided by this particular MODIS daily NDVI dataset. So let me get back to Earth Engine. So in the next step, we're going to mention the time period of analysis. So a time period of analysis starts from 2020 to 2021. So we're going to mention this particular function, dot filter date, start date, and end date. So the start date we have mentioned as 2020, and the end date it is mentioned as 2021. So you can able to see here. So I've mentioned this variable start date and end date. So in the next step, we're going to perform the temporal join of MODIS with the Landsat imagery with a max difference of 3 days. So basically, we are about to temporarily pair each Landsat imagery with one or more MODIS images that are within 3 days of its acquisition time. And this temporal alignment is crucial when integrating the dataset with a different revisit period. For example, the Landsat 8 imagery has a revisit period of 16 days, and the MODIS has around 1 day. So first we have to mention the max difference. That is the number of days. For example, I'm going to mention the variable max days is equals to 3. So I'm going to mention the variable max days equals to 3. So in the next step, we're going to convert the days to millisecond. So to do that, we're going to mention a variable called max difference millisecond equals to earthengine.number max days, that is referring to 3 days, and we're going to multiply 1000, that is the 1000 which refers to 1000 milliseconds, and an hour has around 3600 seconds, and a day has 24 hours. So we're going to mention this dot multiply 1000 multiplying 3600 multiplying 24. So this operation is very essential in order to require it for the temporal operations to be performed in Earth Engine. So we are converting into a millisecond format. So for that, we're going to mention this dot multiply 1000 multiplying 3600 multiplying 24. So here the max stage refers to 3. So it's 3 multiplying the total milliseconds, and the total number of milliseconds for 3 days. So in the next step, we're going to create another variable called temporal filter. So it is so this particular variable we're creating as a temporal filter in order to compare between the two collections, that is two image collection, that is Landsat 8 and MODIS imagery. So to do that, we're going to mention a variable called temporal filter equals to earthengine.filter.max difference. So basically we are using this dot max difference filter. So this max difference filter is a kind of temporal filter, so that are helping us to find the corresponding images within 3 days of difference. So that's how this filter is very useful. So it checks an absolute difference in acquisition time between the left collection, that is our Landsat 8 image, and the right collection, it is MODIS imagery, and filters the image pair where the time difference is less than or equals to the max millisecond, that is 3 days. So in the left field, we know that in the left field, which represents the Landsat 8 imagery, and the right field, which shows us the MODIS imagery. So in this field, we have mentioned the left field, which indicates the Landsat 8 imagery. There is and that we're going to mention the system time start, and similarly the right field, which refers to the MODIS imagery. There is a system represents the system time start for the MODIS imagery. And in the next step, we're going to use this to create a variable called join method. So this defines the join method as a save all, which keeps all the matching MODIS imagery for each Landsat imagery. That satisfies the filter and matched the MODIS images will be saved as a property named as a matched MODIS inside the Landsat image. So to do that, we're going to mention this variable join method equals to earthengine.join.saveAll. So we can join two different, that is, we can join the Landsat and MODIS imagery using this particular join method, that is save all. So this method save all, which keeps all the matching MODIS imagery for each Landsat image, that satisfies the filter. There is our maximum difference based on this filter maximum difference. And further, this matched MODIS images will be saved as a property named called matched MODIS inside the Landsat image. So basically we need to find the MODIS images within 3 days of Landsat image acquisition. So in the next step, we're gonna apply the join operation for the Landsat NDVI is our primary image, and followed by the MODIS NDVI is our secondary image collection. So this temporal filter ensures only an image within 3 days are matched, and the result is a new image collection which will be stored in this variable called matched collection, where each Landsat image now contains a list of matched MODIS images as a property called matched. So the property will be called as a matched MODIS. So for that we define this variable called matched collection equals to earth engine.image collection and the join method referring to this variable, and we're going to mention dot apply Landsat NDVI is a primary image collection and MODIS NDVI is of a secondary image collection, and the temporal filter based on the 3 days interval. So there is this temporal filter which ensures that only images within 3 days are matched, and the result will be the new image collection, but the Landsat image now contains a list of matched MODIS image. So this temporal filter refers to this particular variable where we mentioned the temporal filter condition here. So in the next step, we're going to combine the Landsat and MODIS, that is matched MODIS images for our regression modeling. So for that, we're going to mention a variable called regression input equals to. So before proceeding towards our regression modeling, let us view the details of this particular imagery, that is matched collections. So I'm going to mention as print here, and I'm going to copy this variable that is matched collection, and I'm going to paste it here. So now I have mentioned as matched collection referring to this variable, and I'm going to output the layer name as matched collection. So now we're going to run this and let us view the details in the console section here. So here you can able to visualize we have this image. I'm going to click this arrow. So now in the matched image collection here, so we have a total of around 6 elements here. So now we're going to navigate to features here. So in the features, so I'm going to click one of the image here. So for example, I'm going to click this image, and now we're going to navigate to the properties here. So in the matched MODIS, we have a total of 6 images here. So I'm going to click this arrow. So from here you can able to observe, so for each Landsat 8 image here, so for each of the Landsat 8 image there is a new property called matched MODIS. So for example, here you can able to observe for each of this Landsat 8 image, so we have all of the MODIS NDVI bands within 3 days. For example, we can consider as this particular date 24/8/2020, and here the Landsat 8 image you can able to say it is August 2022 is 2022 August 2020. So this is the date of Landsat 8 image. So as you can able to see here, we have the August 2022 and August 2023 and August 2024, 2021. So the Landsat 8 image here, the date is 22 August 2020, and you can able to observe this matched MODIS imageries. So it contains a similar matched images, dates, similar matched dates. For example, 22 August 2020 and 23 August 2020 and 24 August 2020 and 21 August 2020. Likewise, you can able to observe the matched MODIS images here for each of the Landsat 8 images. So there is after and before that date within 3 days it gathered together, and now I can get a maximum value from these from these image to make to get a cloud free image and added as a new band next to our Landsat 8 image, the Landsat NDVI image. So in the next step, we're going to combine the Landsat and matched MODIS imagery for regression modeling. So before proceeding towards, we're going to create a variable called regression input. is equals to matched collection. So the matched collection contains the Landsat images, where each one has a list of temporarily matched MODIS images, which has we have done from the previous join step. So now we're gonna create a map function here, that is dot map function image. So in the next step, we're gonna create another variable inside this loop called MODIS stack equals to, so image dot get matched MODIS. So which means that it's gonna extract the a list of MODIS images, and after that we're gonna mention earth engine dot image collection dot from image. So it's gonna convert the list of image to a image collection. So for that we mentioned earth engine dot image collection dot from image, and last we have mentioned dot max function. So it reduces it to a maximum NDVI pixel value across the matched MODIS image, for example. So the max function here, is used to compute the single composite image by taking the maximum NDVI value at each pixel from all the matched MODIS image. So taking the maximum NDVI value helps to reduce the cloud contamination and shadow effects or the noise pixel. So this is based on the simple logic that is greener is cleaner. So using a maximum NDVI value, so it's going to give us a clean and high signal NDVI. So which is very useful for improving the quality of fit for our regression model. So for that we are using dot max function here. So in the next step, we're gonna return this return image dot, and we're gonna mention dot add bands MODIS stack. So MODIS stack refers to this particular variable here, and we're gonna rename it as NDVI MODIS. So the add function adds the NDVI MODIS band to its original Landsat image, and the result it's gonna give us as a new image collection with two key bands, that is NDVI MODIS, the coarse-resolution, and NDVI Landsat with a fine resolution. So next we have applied the linear regression using MODIS NDVI and Landsat NDVI. So now to apply our regression model, we're going to define a variable called regression is equals to regression input dot map function. So the regression input which represent this particular variable here. So represent this particular variable regression input, and we're going to apply a map function dot map function image. So now in order to calculate the linear regression model, so we need one constant band next to the dependent and the independent variable. So in order to get the precise output from the model, so for that we're going to create a variable called constant equals to earth engine dot image dot constant with the value number 1, which indicating the constant band. So next we're going to mention the function returning an independent and dependent band. So for that we're going to mention return image dot select NDVI MODIS, and we're going to mention to add this band, we're going to mention dot add bands constant, and further to add our NDVI Landsat, we're going to add that band using this function dot add bands image dot select NDVI Landsat. So for each image we're going to select NDVI MODIS and the NDVI Landsat, and we're going to add a constant band here, as it required input for the intercept term in the linear regression. So here the independent and dependent variables are, so the NDVI and the constant band, it is the independent variable, and the NDVI Landsat is the dependent variable. So in the next step we have to perform the linear regression between the independent and the dependent variables. So first for example, the independent variable, which includes NDVI MODIS and the constant image, that is two predictors, and the NDVI Landsat is the dependent variable. So to perform our real linear regression between the independent and dependent variable, we're going to mention dot reduce earth engine dot reducer dot linear regression. So this is our linear regression model, and inside we're going to mention num(x) is the total number of the independent variable, that is 2, and the num(y) is the total number of dependent variable, that is 1. and the output is it's going to be a single image with a regression coefficient stored in the two-dimensional array band called coefficients. So now to view this details about this particular image, we're going to mention as a print regression, and output is going to be the regression model. So now we're going to run this code here, and now let us visualize the result here. So I'm going to navigate down here. I'm going to click this arrow, the regression model, and I'm going to click this bands. So in the bands we have a code. So here you can able to see that we have one images with two bands. So one of the band is a coefficient, and another band is a residual. So the coefficient band has two dimensions here. So the one dimension which represents the refers to gain, and also the other dimension it is related to the offset, and the gain which shows us the slope of changes. So basically the gain which shows us the slope of changes between the dependent and the independent variable. So here we need to have or to extract the gain and the offset from the coefficient. So first for the gain will be represented as a slope, and the offset will be represented as an intercept. So next, to perform our regression, in order to our linear regression model, we required the two important parameter, that is slope or the gain. So slope and gain, which represents the same term. So similarly, the offset and intercept, which represents the same term here. So first we required the slope and intercept. So I'm gonna mention the variable called slope is equals to regression dot select coefficient dot array get. So it is an array structure, and in one dimension. And the next is we're going to define another variable called intercept is equals to regression dot select coefficient dot array get is our second dimension. So first slope, which represents our first dimension, and the intercept, which represents our second dimension. So the first dimension it's going to be our slope, and the second dimension it's going to be our intercept. So basically it's going to extract the slope coefficient for NDVI MODIS and the intercept coefficient for the constant. So these will be used to apply the regression model to our MODIS dataset. So these parameters are the main parameters for our prediction model, the slope and the intercept. So now the gain, that is slope, and the intercept, it is created and extracted. So the next step, we're going to downscale the MODIS NDVI to a 30 meter using our regression model. So to downscale our MODIS NDVI to 30 meters, so what you need to do is applying these coefficients, that is our slope and intercept. So that is our slope and intercept on the MODIS images to get the high resolution MODIS NDVI image. So to do that, we're going to define a variable called MODIS 30 meter equals to, and we're going to refer the original MODIS image, that is MODIS NDVI, and we're going to apply a function, map function here, dot map function image. So we created this function in order to apply the linear regression model on each existing MODIS NDVI image. So in the next step, we're going to define a variable called predicted NDVI is equals to image dot multiply. So we're going to apply this formula here, that is the NDVI 30 meters. So we're going to apply this formula called slope multiplying NDVI 500-meter resolution plus intercept. So the slope and the intercept is the coefficient, and NDVI 500-meter is the MODIS NDVI image. We are applying this formula here, that is image dot multiplying slope dot add intercept, and last we're going to rename as NDVI 30 meters. So this is the prediction model to reach the MODIS NDVI, the 30 meter spatial resolution. And last we're going to return the image, and we're going to rename as NDVI 500 meter image, and we're going to add this predicted NDVI image using dot add bands predicted NDVI. And last we're going to mention the copy properties, image dot property names, which keeps the temporal metadata for future for charting and or exporting the image, and the NDVI 500 meter, which refers to NDVI 500 meters, which refers to the original MODIS imagery, and the predicted NDVI is the NDVI 30 meter resolution. Now in order to view the metadata property of this particular image, that is MODIS 30m, I'm going to mention as print, and I'm going to mention the variable name is MODIS 30 meters. I'm going to paste it here. So I have mentioned MODIS 30 meters. So now we're going to run this code here. Let us visualize it in the console section. So now in the console section, I can able to visualize here. So I'm going to click this arrow. So now we have a total of around 366 elements. So now I'm going to click this option called features, and I'm going to select one of this imagery. So in the band section, in the bands, we have two elements here. There is two bands. So one of the band is NDVI 500m, and the second band is NDVI 30 meters. So in the last step, so in the next step, we're going to add this layer, that is our MODIS 30m. So to do that, we're going to define map.add layer MODIS 30m dot two bands. So it's going to stack all the bands, all the images, and we're going to mention based on a study area, that is dot clip, based on our region of interest, that is study polygon, with the default visualization parameter, and we're going to output the layer name as downscaled NDVI 30 meters. So now let me run this code here. I'm going to run this code, and let us visualize it. So now I'm going to navigate to the layer section, and I'm going to turn on this downscaled NDVI, and I'm going to turn off this. So now the image has loaded up here, and now we're going to navigate to the layer. I'm going to click this option. So we're going to select single band, and they're going to select this particular month, that is in July. So you're going to select 2020 July of NDVI 30 meters. You're going to select this, and I'm going to navigate to the custom section. I'm going to select stretch 90%, and now we're going to click apply. So the image is getting loaded up here, so you can able to visualize our downscaled NDVI from 500 meters to 30 meters. I'm going to close this. Let me turn to a satellite mode here. So now we visualizing the downscaled NDVI of 30 meters, and you can select a suitable month of your choice. You can select for example 500 meters of MODIS image, and downscaled NDVI 30 meters. You can select any month of your choice for this year. So for example, I'm going to select for July here. So I'm going to select this, and I'm going to choose to because the custom section I'm going to select stretch 90%, and now we're going to click apply. And now let us visualize the downscaled NDVI during July 2020. I'm going to close this. So during this month, you can able to see the vegetation is pretty higher compared to the February. So you can able to see the difference here. So next step, we're going to validate this particular downscaled image using our NDVI time series analysis. So to do that, we're going to define ui.chart.image.series MODIS 30m, referring to this particular variable, and observation point. So I'm going to fix my observation point over this particular farmland here. Let me show you that. So you can able to see the point I have mentioned here for this particular farmland here. You can see this particular point here. This is my point data, and I'm going to turn on this downscaled NDVI for this particular farmland. So now I'm going to visualize the NDVI value of NDVI 500m versus NDVI 30m downscaled imagery. So I've mentioned as observation point, and mentioned a reducer or earth engine dot reducer dot first function to get the first value out of all the results, and they're going to mention the 30 meters. And additional options are going to mention as dot set options. Title is MODIS NDVI downscale to 30m via regression, and h-axis is the date, and v-axis is the title, NDVI value, and line width and point size. And you can set the colors to it according to your choice. For example, I'm going to select to a red color, this color palette which indicates red, and the predicted one which indicates the color palette, it's going to be green. So we're going to run this code, and now let us visualize the result here. So the title is NDVI MODIS NDVI downscale to 30-meter via regression, and this axis represents the NDVI value, and this particular axis represents the date, and the color. So the green color which indicates the NDVI 30-meter value, and red color which indicates the NDVI 50 meters. So from this graph you can able to see the fit here. So the NDVI 30-meter versus NDVI 500-meter. So the fit is kind of okay, it's not so good. So you can take a closer look here. I'm gonna click this option. So in the first section, the NDVI value matches correctly with the MODIS 30 and 500-meter matches here. For example, towards this right side of the graph here, it kind of matches. But the central part and towards the starting section here, the NDVI value is kind of mismatching with the NDVI 500 versus 30 meters. So we can also use the other formula in order to view the difference between NDVI 30 versus 500. We are specifically selected this particular formula here, so this particular area. So in this particular formula, you can also select different point data in different formulas, and you can view this difference between the NDVI and the NDVI 30 meters versus 500 meters. So in this video, I have shown you how to downscale the MODIS NDVI 500-meter to a 30-meter resolution using machine learning approach in using Landsat 8 imagery in Google Earth Engine. So thanks for watching, and make sure that you subscribe to our channel and give us a like. And the code description will be the code link will be given in the description of this video. So thanks for watching.